Okay, I'll wait for 2 more minutes and then we can start. Okay, I think it's safe to start now. Uh, is my screen visible to you all? Can you see the PDF?
Yes, sir.
Okay, so this is tutorial number 11, and mostly we will be looking at questions on how to design filters or discrete time filters to be more specific. And in the fourth unit, but in the end of fourth unit, we looked. There were some concepts like impulse invariance, which was discussed, and also windowing. So we will be covering those in this tutorial. So let me start with question number one. We have this continuous time impulse response. The system function corresponding to the impulse response. So whenever we have an impulse response in the continuous time like this, I take its Laplace transform and I have got this capital HCS. Now the first part of the first question says that we have to use impulse invariance to determine H1z for a discrete time system such that H1n is equal to HCNT. So basically we have to find out the discrete time counterpart of this continuous time system, and then finally we have to take it z transform to find out this h1z function, and in doing that we have to use the impulse invariance, which basically means this one, that we have to substitute the time variable t as nt, and that's how we will obtain the discrete time counterpart, and then we can take the z transform to find out this. Okay, so let's look at the first part first, and then we will come back to the part B. So the solution is here. So we have this HCS given to us, and we will apply partial fractions. And on doing so, we can decompose it into these two parts, each part having a single root or a single pole. So these two parts we will get, and we can find out a and b using the partial fractions method. And you will, when you find that out, you will see that both of them are actually zero 0.5. Now, once we have this decomposition, now it is possible for us to take the inverse Laplace transform to find out the continuous time HCT. So for that, we will now look at this Laplace relation that so we can directly do that. And we note that whenever we have e raised to the power minus at ut, then corresponding to that, the Laplace transform is of the form 1 by s plus a. So it means that it will have a transfer function with the pole at s is equal to minus a. So using the same this formula, we can see that this part corresponds to an e raised to the power minus uh, a plus j beta t ut, and zero 0.5 will be in the multiplication. So HCT can be written as 0.5 times e raised to the power minus a plus j beta t, and similarly this one will be a minus j beta t, and this ut will be there. So this is the inverse, simply the inverse Laplace transform, and we have found out this HCT. Now that we have this HCT, we are interested in applying the impulse invariance. So we will say that H1n is obtained by replacing small t with n times capital T. So that directly gives me this expression. And here you can see that t is replaced by nt. And now I have to take, so I have got the discrete time sequence by applying this impulse invariance. Now I can take the Z transform, and it's quite straightforward actually, because we know that whenever we have any such term, we can write it as 1 by 1 minus AZ inverse, right? So that will give me zero point 0.5 is in the numerator. This will be 1 minus this term e raised to the power minus a plus jb times t into Z inverse. Okay, so this is just like a raised to the power n un, right? Similarly, this is also a raised to the power n un, and that's the particular relation that we are using to find out this h1z. And this is the region of convergence, mod z greater than a, right? With this, we have got h1z, and that was what the question 1 asked for. So we have got this h1z. It was straightforward. We just took inverse Laplace transform followed by z transform, followed by impulse invariance, and then the z transform. Okay, coming to the part 2, now it says apply step invariance to determine h2z. Now the step invariance term is new, but it is actually nothing but, instead of using the impulse response, we will use the step response, which is denoted by this st, and we will apply this invariance property here to obtain this discrete time system, which is h2z. And it has been given to us that s2n is the summation minus infinity to infinity of h2k, which means that if you have the impulse, let me start with this equation actually. If we have the impulse response, I take its integral from minus infinity to t, I'll get the step response, right? And similarly, so that's actually understood. If you have an impulse response, and you just, or if you have an impulse and you take an integral of that impulse, a simple impulse function, then obviously we will get a unit step function. And so that is what this equation represents. And similarly, when we have the corresponding h2k, which is the sequence corresponding to the impulse response, and we take the summation, because now we are in discrete time, so we will get this s2n function, which is the step response, but the sequence of it actually. So we will use this to find out h2z. So again, let's look at this one. So first of all, this one is given to us, and so a nice property of dealing with the in the frequency domain is that the integral just becomes a division in the frequency domain. So that means that if I take the Laplace transform of both sides, I'll get SCS on the left hand side, and on the right hand side there will be this integral of this term. So I can write it as HCS divided by S, where S is the Laplace variable. So that is one of the reasons why Laplace or any frequency domain analysis is so good, because this calculus function is converted to simply a expression, an algebraic expression. And similarly, if there was a derivative, then that would have become a product with the Laplace operator S. So we just applied this Laplace, and we got this thing. Now we already know HCS from the previous part, and SCS will be that divided by S. So whatever term we had last time, we just divided by S, and then again we take the partial fractions, right? Because now we have to apply the impulse invariance in this step response. That is why we are doing this. So Again, applying partial fractions corresponding to each of the pole, we will have uh, one term, and obviously the term corresponding to s plus a minus j beta will be the complex conjugate of the term which is for s plus a plus j beta, right? Because these two roots are also complex conjugate of each other. So again, on applying partial fractions, these will be the a1 and a2 values that will be obtained. But for the rest of this question, we will just use a1 and a2 and not write the whole thing. Now, once we have got SCS, we will apply this again, this step invariance property to get S2n, right? So S2n is just replacing small t with n times capital T, and so we will get some S2n, and then from S2n we will have to take the Z transform of this term S2n to compute S uh, in the z domain, right? Just like we did in the previous case, but in the previous case we had h. So one, I have skipped one step here, and I have directly noted that all the poles of this transfer function must transform as this: zk is equal to e raised to the power skt. So that was also what I did in the previous part, by the way, that I could directly say that if I have to jump jb or minus of a plus jb, so that is what will be here in the power of e in the z transform. And that is just one observation that I am directly using here to find out S2Z, the Z transform. I'll say that, so let's say if I'm talking about this part, S2, sorry, A2 by S plus A plus JB. So this will directly become A2 by 1 minus AZ inverse. And that A is e raised to the power minus of A plus JB times T, in the similar way as in the part A. And there is one term E1 by S, and so what for that will correspond to this 1 by 1 minus Z inverse, and finally the last part which will give me this. So now essentially I have taken the inverse, um, uh, I have taken the inverse Laplace transform, applied this impulse invariance, and then taken the Z transform to obtain this S2Z. Now remember that I am interested in finding out H2Z. So for that, I will again note that this is the relation between the discrete time sequences. This is the step response sequence, and this is the impulse response sequence. And this one I can also write as the convolution of the H2n with this UN, right? Because when I this is the impulse response, and step response is nothing but when the input is a unit step and the system is represented by the impulse response, right? So the convolution of both of them will give me the step response. Using this observation, we can take the Z transform of this expression S2n is equal to H2n convolution with UN. That will give me S2Z, and on the right hand side I will get this term, right? So this is S2Z and H2Z's relation. I was interested in finding out H2Z, and I already have S2Z. So I can just say that H2Z is this term. So that means I have just multiplied this S2Z with 1 minus Z inverse. And for this, the numerator and denominator will cancel out. And for all the other terms, it will be present here, right? Because with A1, I had 1 minus Z inverse in the denominator. So with that, I'll get H2Z, and I can also write down the region of convergence, which is mod Z greater than real part of A, and that is why there is only e raised to the power minus A times T. So this was the first question. I hope this question is clear to everyone. Uh, So are there any doubts? Anyone? Someone should reply whether they have doubt or not, so that I can proceed.
No, sir. There's no doubt.
No, sir.
Okay. Okay. Okay, then I'll move to the second question. In this question, we have a system function. Again, a discrete time function is given to me, that is this h of z. And I have been told that to assume that this discrete time filter was designed by the impulse invariance method, where TD is 2. That is, when I take this Hn, which was, so basically just like this, I had H1n equals to Hc and T, and this T is actually what they are calling as TD. Also, when I do this, I multiply this Hc with the magnitude with a magnitude of 2. Obviously, that won't make much difference to the sequence, but that is how impulse invariance is used. So that is why this is done here. And it is given that HCT is real. I have to find out the system function HCS, which is in continuous time, of a continuous time filter that could have been the basis for this design. And it's asking if my answer is unique or not. So basically, in this question, we have this hz, and and they're saying that if I had some system function which was in continuous time, on which I had applied this impulse invariance and then gotten this system h of z, then what is that system function? That is basically what this question says. So let's see. Let's see the first part. Okay, so in this part, it's here. So first of all, the thing that we noted in the previous question was how does the poles of the continuous time system and the z transform relate. So this was the relation, that zk is equal to e raised to the power sk times td. Okay, that means that if I have we already know this, that if I have 1 by s plus a, then that would mean e raised to the power minus at ut in the, after taking the inverse Laplace. And when I do this with the inverse Laplace, I will apply the impulse invariance by saying that t will be replaced with n times capital TD, and that will give me this part over here, right? And then so if I combine these two parts, I can simply say that if I have something like 1 by s plus a, then that would directly in the z domain become this. There will be some TD term, because we are also multiplying the magnitude with TD, as you saw in the question, and then there will be this part in the denominator. So 1 minus this part to z inverse, right? So this relation is quite useful for such kinds of problem where we are dealing with impulse invariance design. And now this is h of z that has been given to us. Now our job is to map this back to the s domain, and you can see the relation between this part and this part. So this part clearly tells us that uh, TD is 2, right? And ATD is equal to 0.2. So with that, I can tell that, so first of all, the first thing I need to do is, I need to, when I go from the Z domain to the S domain, is I have to divide the numerator with the TD, because here it is 1. So I just said 2 by TD, and TD is actually also 2. Then I will have S plus A. and you can calculate a because 2a is equal to zero point 0.2, right? So 0 0.2 by td is what a is, right? And that means this is 0.1. Similarly, with the second term, I will divide by td in the numerator. I will say that a times td is equal to zero point 0.4, from where I can write a here. And on solving this, I'll get this as HCS. Now, it was also asked whether or not the above solution is unique, and the answer to that is that it is not unique. That it does not mean that only this HCS can give us this HZ, and that is because this Z is periodic. The variable Z is periodic. It is actually e raised to the power j omega. In the Z domain, we are uh, moving in the unit circle, right? And that is why a more general solution would be if I write it like this. So I have included this term j 2 pi k by td, and similarly j 2 pi l by td, where k and l are integers, and this will be the most general form which will give us this type of h of z. So this is the general case, and the one we are dealing with is when k and l are 0. And the solution HCS is not unique corresponding to an HZ. So there would be multiple continuous time systems which can have the same discrete time system model HZ. Now let's look at the second part of this question. It says that Hz was obtained by the bilinear transformation method with Td is equal to 2. So again, we have been given that Td is equal to 2, but now they are saying that a bilinear transform method is applied. And this is one of the method that was discussed in the lecture, but we will also shortly, briefly look at it. Now it says, find the system function HCS that could have been the basis for the design. So similarly to the previous case, but now we do not have impulse invariance, rather we have a bilinear transform method. Again, TD is 2, and we have to find out the system function which is in the continuous time, which could have been basis to design this HZ. So let's look at this part also. Yeah. So first of all, what we need to recall about bilinear transformation is that essentially what we are doing is that we are mapping the frequency in the continuous time to the frequency in the discrete time, small omega. Frequency in the continuous time is infinite, which means that it varies from minus infinity to infinity. But for discrete time, the frequency is between minus pi to pi, so it is finite. And the relation that we will use, and that we also saw in the lecture, is that S is related to Z like this. So unlike the case, the general case where we just say that capital omega times TD is the small omega, here we have this relation between the S and Z variables. And this is the basis for, this is the main thing about bilinear transformation. So we can also put Z as the subject, or we can find out Z in terms of S, which will be this part, right? We have been given this H of Z, and when I replace this Z with this part, then I am basically doing the bilinear transformation. So I have substituted Z with S here, and TD is 2, so this part just becomes 1, and Z will be 1 plus S upon 1 minus S. And you see that I have replaced Z inverse with 1 minus and S upon 1 plus S. That will give me, upon some calculations, I have just multiplied it with the numerator and here to give me this part. Then finally, here I have taken 2 by 1 plus e raised to the power minus 0.2 as common from this part, which will give me this part. And from this second part, I have taken 1 by 1 plus e raised to the power minus zero point 0.4 common. So the numerator will remain same. It will become s plus this part divided by 1 plus e raised to the power minus zero point 0.4. So this is HCS that we have obtained. So finally, again, it is asked from us whether this representation is unique or not, and the answer to that is that this is unique, because bilinear transformation will always give us a unique representation. We cannot find out two continuous time systems which could be the basis for design of the discrete time system. So that is one thing to keep in mind for bilinear transformations. Finally, okay, now let's go to question number 3. This is a short one. It just says that we are interested in implementing a continuous time low pass filter, which is this H J omega, and to do that we will use the system as shown in figure. So this figure is this. So you may remember this figure from the previous chapters. This is basically how we will implement any continuous time system. There is a C2D converter before the discrete time system that we have found out, and after we will have a D2C converter, and this overall system will be continuous, which means that its input and output will be continuous. So we have already seen this, right? Now what it is saying is that, so we want to implement a continuous time low pass filter, and we are doing that, uh, and we have been given the discrete, and the discrete time frequency response is given by this, right? And other things that are given to me are the sampling time 10 to the power minus 4 second, right? And the input signals frequency response, which is this. So it is said that the input signal is band limited, and this is how it is band limited, right? And these are the specifications that are given for the continuous time frequency response. And it says that we have to find out the corresponding specifications on the discrete time frequency response HD, right? So when I have to implement this system as a discrete time LTI system, because this block is discrete time, what I need to do is I need to convert these specifications which are in continuous time to the discrete time. So let's look at how that is done. Okay, so here is the question. Now the first thing that you need to remember is that this is the simple relation how this the frequency variables are related for the discrete time and the continuous time. So this, in this discrete time, the small omega is capital omega times capital T, where T is the sampling rate. So first thing that so let's first go back and quickly look at this. These specifications. So these are specifications for a low pass filter. What does that mean? It means that between 0.99 to 1.01 of magnitude, this will be the magnitude of this for all frequencies that are between minus 2 pi into 1000 to 2 pi into 1000. And this one, the second one, is about the stop band. It says that after this frequency, it does not allows any frequency in the frequency range. After this, nothing can be passed, right? While in this frequency range, that this is basically the pass band, and this one is basically the stop band of the low pass filter, right? So first of all, 2 pi into 1000 and 2 pi into 1100. So let's convert this directly to the discrete time, and that can be done using this relation, because we know that T is 10 to the power minus 4. So I can find out small omega as 2 pi into 1000 times 10 to the power minus 4. That will give me small omega, which is in radians. And this is for the pass band, right? This is the pass band cutoff frequency. Similarly, there was also one specification in terms of the stop band cutoff frequency, and that is 2 pi times 1100. And we will just multiply it again with t, which is 10 to the power minus 4 seconds, and that will give us small omega in 0.22 pi radians. And now we can write down the specifications for the discrete time, which will be the magnitude was between 0.99 to 1.01, but now this magnitude is for the discrete time frequency response, and that is for frequency between 0 to 0.2 pi. Similarly, these are the stop. This one is the stop band specification, which is basically that the magnitude of the frequency response is less than or equal to 0.01 for the frequency between 0.22 pi. So 0.22 pi is what we calculated, and up to pi. So we can say that the upper limit will be pi because we are in discrete time. That's the maximum possible frequency. In the continuous time, if you remember, there was no upper limit, and that was because because capital omega goes to infinity. Okay, so that is question number 3. Let's look at this one, question number 4. Okay, but before that, are there any questions, any doubts, any queries? Any doubts? Okay, I guess this everyone in this tutorial is an introvert, so right, you can comment if you're not interested in speaking up. Let's go to question number 4. Now I have been again given a continuous time low pass. By the way, I have taken this question from the Oppenheim book, so you can try these some of the questions from that book. Don't go into the advanced sections because those questions are a little bit more difficult. So the easier ones that are related to these you can solve from that book. And okay, now coming to question number 4. Suppose that we are given a continuous time low pass filter. So just like in the previous case, we have a low pass filter, and this is how its frequency response is. Now this gives a much clearer picture, because now the first specification is that the magnitude of the frequency response must be between 1 minus delta 1 to 1 plus delta 1, and that is for all the frequency in the pass band, which means it is from minus omega p to plus omega p. Similarly, this is the stop band, where it says that the magnitude of the frequency response is less than or equal to delta 2 for frequency omega, which is less than omega s, right? And now it is saying that we are interested in the discrete time. We want to so the discrete time low pass filter that will be used to implement this continuous time low pass filter is obtained by using this transformation, and this transformation is 2 by td multiplied with 1 minus z inverse upon 1 plus z inverse, which is nothing but the bilinear transformation which we just saw. Now there are a few parts that are asked from us, but before going into this part, I'd like to show you this how the specification look like for a low pass filter. So I have a diagram over here, which is this one, and this is for the continuous time case, but a similar kind of picture is also for the discrete time case. So here it is saying that if this is 1, then from 1 plus delta 1 to 1 minus delta 1, this is how I want my response to be between these two values. And this is up to a frequency which is the pass band. Then when we come to the stop band, which here I want that the frequencies vary between minus delta 2 to delta 2. So the response would be that we start somewhere here, then it goes down like this, and then it stays within this one. So here you have ensured that the higher frequencies won't pass because the magnitude is quite low, right? It will remain somewhere here. And you have ensured that the lower frequencies, especially frequencies up to this omega p, can pass through the system, right? And this diagram is particularly called the tolerance scheme. And this one is for the low pass filter, an ideal low pass filter. Now let's look at the questions. So the first one is about, so the questions are actually quite straightforward. The first one says, if we fix omega p, which means that we have fixed the passband frequency, and we want to find the value of td such that the corresponding passband cutoff frequency for a discrete time system omega p is pi by 2, right? So we have been given small omega p, which is for the discrete time system. We have been told that capital omega p is fixed and we have to find out td. Now there is another relation that we will look at to solve this thing, and that is how the frequency maps in case of bilinear transformation, and this is that result. So this is also an important result, and so you can see the difference here, that when we had just the impulse invariance case, we had capital omega times td is equal to small omega. But now for the bilinear transform, this is the relation, right? So if I substitute capital omega as capital omega p, then the small omega must be replaced with small omega p, right? This is the continuous time passband frequency, and this is the discrete time passband frequency. So it is told to us that capital omega p is fixed and we have to find out td. So I just make td as the subject. This omega p goes in the denominator, it becomes tan. In the question it was given that small omega p is pi by 2. That would make this pi by 4, and tan pi by 4 is 1. So this just becomes 2 by capital omega p. That's the part A. Coming to part B, it says that now capital omega p is again fixed. We have to plot small omega p as a function of td. Okay, so let's see. So now we have capital omega p is fixed. I have again used the same relationship as this one. I have taken td to this side. Capital omega p is fixed. I am trying to make omega p as the subject so that I can plot it versus td. And in that case, I will get this relation. Now, how do I plot td versus omega p? So you can see that the relation is tan inverse. So an arctangent relation means that it will let's, you can just take td as 0 and infinity and see. So for 0 it will become 0, omega p will be 0, and for infinity you will get pi, right? Because this will be pi by 2 and it is multiplied with 2. So omega p will be pi. So that means that this will asymptotically go to pi, right? And that means so the significance is that as you vary the td, which is the sampling time or the time that you use for that transformation, then the omega p, which is the frequency in the continuous time, will approach to uh, its maximum value, which is pi. Now let's look at the third part. Now it is saying that both capital omega p and capital omega s are fixed. We can now sketch the transition region. So we have to sketch the transition region, which is delta omega, which is omega s minus omega p, which is the stop band frequency minus the pass band frequency in the discrete time. And we have to plot it versus td from 0 to infinity. So let's see what how this looks like. Okay, so now given to us was that capital omega p and capital omega s are fixed. We can again use this relation that we found out in the previous case for omega versus capital omega and TD. So we can use it for both the stop band frequency, and so in that case here will be capital omega S. For pass band frequency there will be capital omega P, and these are the two relation. So when I take their difference, that is basically the transition range or the transition frequency, right? And that delta W will be this subtracted by this, so the expression will be this one. Now I have to plot this one with respect to the variation in TD from 0 to infinity. So if I put both of them as 0, obviously delta omega will also be 0. Let's say I put both of them as infinity, I will get uh, pi by 2, pi by 2, and they are subtracted from each other. So delta omega will again be 0. So if I plot this, you will see that delta omega versus TD looks something like this. We start at 0, it increases a bit, and then it goes down to 0. So the transition width actually goes down to 0 as we keep on increasing the TD. Again, we can also look at this, the significance of this, especially using this diagram. So the transition width is basically the difference between this omega s, capital omega s, to capital omega p. Although we were looking in discrete case, but it still makes sense. The difference between these two is the transition width, because it tells us how quickly we are transitioning from the pass band to the stop band. So basically it said that if we increase the TD, the value of TD, while keeping all the other parameters constant, there will be a sharp change from this band to this band, which means that we will quickly be converging. And that would mean that omega P and omega S are very close to each other. And that is why this width will be very small. So that is the significance of this part, right? This one. Okay, now we have only one question left. Let's look at this one. And this one is, it has to do with windowing, right? This is a very important concept. So here we have an FIR low pass filter which is satisfying the specification this, right? Now we are talking about FIR low pass filter, so keep that in mind. Windowing is applied for FIR filters. We have been given some specifications in the discrete time case, and it is said that we are achieving these specifications by applying this window Wn to the impulse response HDN for the ideal discrete time low pass filter with a cutoff omega c is equal to 0.3 pi. And we have been given a number of windows, and we have been asked which of these windows will meet the specification, which means that which of these windows is suitable for achieving these specifications in the discrete time. For each of the window that you claim will satisfy this specification, give the minimum length m plus 1 required for the filter. So we also have to give what is the length of the filter, right? So let's look at this one. Now these were the filter specifications that were given to us in the question. So let's look at these filter specifications. So since we are talking about low pass filter, so remember we saw in the previous example that there is this 1 plus delta 1 to 1 minus delta 1 to 1 plus delta 1, which is the range of magnitudes. So this is some tolerance, some error tolerance delta 1, and we were saying that from 1 minus delta 1 to 1 plus delta 1 the response should be. And similarly there was some delta 2 such that between minus delta 2 to delta 2 the response should be in the stop band, right? So using the same thing, we can find out this for the pass band error del p. So this is corresponding to that 1 minus del p and 1 plus del p. So for that the error, that is del p, is basically this, let's say this value 1.05 minus 1. That's how we can find out this delta. And similarly, there was delta 2, which here is the maximal stop band error, delta S. And that is just given to us 0.1, right? Because in the stop band, we have from minus 0.1 to zero point 0.1. So we have calculated these two parameters first. Now, in the table that we will see quickly, this one, we have been given a number of windows and we have been asked which one of these windows is suitable for us. And for that, we have been given this peak approximation error, which is in decibels. How do you compute something in decibels? You just take 20 times the log of that quantity. And so basically we have to ensure that the peak approximation error of this matches with uh, the desired specifications. So let me, now that I have delta P and delta S, let me calculate these values in decibels so that we can compare. So in decibels, I just take 20 log of 0.05 and 20 log of zero point 0.1 to get these two values. Now, let's look at which one satisfies these two values. So that means from these two values, I can tell that the peak approximation error should be less than this minus 26 decibels. And if we go back to the table, then you can see that minus 44, minus 53, and minus 74, these three values are actually less than that error that is desired. So that means that these three filters, the Han, Hamming, and Blackman filters, or sorry, the windows, are actually suitable for us to design that filter. So we will proceed with these three types of windows. So as written down here, the Hanning time, the Hanning, the Hamming, and Blackman windows are the one that are suitable for our case, and we will use these ones. Now the second part was to find out what is the length of the filter which will result after this windowing of these three windows. So the length of the window is basically how long the impulse response is. Because the resulting filter will be an FIR filter, we know that the length is finite, and in fact that length is equal to capital M plus 1. Okay, so what we have to note here in order to find out the length is that the width of the main lobe is almost the same as the transition width of the discrete time filter. The width of the mean lobe is one of the characters of the window, and that is almost equal to the transition width, which is Ws minus Wp, the stop band frequency minus the pass band frequency. And the width of the lobe is given to us, the approximate width of the mean lobe, which is given to us in this window, which is 8 pi by m for Han and Hamming, and for Blackman it is 12 pi by m. So using this, and by noting the fact that this is almost equal to the transition width, we note that, so first of all, let's just calculate this transition width. It's simply omega s minus omega p. From the specification, this is omega s and this is omega p. So it is 0.1 pi, right? The difference. So this is the delta omega. Now I just equate this delta omega with the approximate width of the main lobe of these windows. And when I equate these, I can find out this m. So for Hanning and Hamming windows, it will be m is equal to 80. For Blackman window, it comes out to be m is equal to 120, which means that the length of each of these three, the filters resulting when we use these three windows will be 81, 81, and 121 respectively. And that is how we have found out the suitable windows and the length of the resulting impulse response. And this was the last question. With this one, we reach the end of tutorial 11. So, do you guys have any doubts?
No, sir.
Okay, 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 great. This is it. So these are the type of questions from these two topics, and uh, these will be the kind of questions that you will see in the quiz. Sorry, I mean the final exam also. So mostly it's just these about conversion, about impulse invariance or windowing. So I would suggest that you practice these type of questions, especially the last ones, because I just covered one question on windowing. So you can practice some of these questions, and that's it. That's the from these topic only. These types of questions are mostly there. So thank you for joining. If nobody has any doubt, then we can end this meeting. Yeah, you can now leave this meeting. Thank you.
Thank you, sir.
Thank you.